Hello Podsters, welcome to third episode of Pod Chat. Let's dive into the conversation of Ankush and Shivam. Today they'll be talking about gamma ray bursts and neutron stars.
Thank you so much for having me here and agreeing to
Thank you
have
for
this
having
talk
me
with
as
me.
well. Thank you for having me. Yes.
Can you give a brief introduction of who you are and what you're currently doing, what you're currently working on?
So, who am I? My name is Ankush, and I like to look at stars. If that's something that I do like to.
And hold up, you get paid to do that?
Yeah, that's a
You get
beautiful
paid to
thing
do
about
that?
it. Like we get paid to look up. That's the most beautiful thing. And apparently, we can convince people. That's the entire thing about astronomy is that you try and convince people to pay you do what you love doing, which is look up all day, all night. But we sleep during the days, so yeah.
So how did you get into this?
How did
Of
I-
looking into the star business?
Yeah, so the first time I still remember, the first time I looked at the Milky Way galaxy, that was the moment, that was I think so around 11, 12-ish years ago. And that's where I realized that, okay, this is something that I would like to dedicate my life, like learning about it. And I still remember it was at this place called Saralma. And I still remember the first time I saw, I literally cried at that moment.
Wow.
Like tears came out because see, then again, you look at city folks. So I've been living in the city for all my life. I still do, unfortunately. And we don't see the stars, right? We look up and all we can see is probably one star, which is the chances of that star being a planet is pretty high.
Yes.
So we can't even see stars. We probably see planets. Morning star, that's actually a planet, Venus. Like for a city folk to go out there and look at the universe or what humans thought of, as their universe, that is at one time, this is a fact actually, look it up. Einstein used to believe at that time, they used to believe in like the whole scientific community used to believe that our galaxy is the only galaxy.
Yes.
And Herschel had like a lot of free time in his hand, so he drew the map of our galaxy with sun in the middle.
And this is the William Herschel that we are talking about.
Yes. That thing sort of carried on till Einstein, till Hubble came along and discovered that these things that we call nebulae out there, or the more technical term for it would be spiral nebulae, are actually galaxies outside a galaxy. So they were their own pocket universe. So probably that's where the idea of multiverse came into. But yeah, I mean that was,
And then eventually people realize that it's not pocket universes. It's just one big universe and a
yeah,
lot of
and
galaxies.
There are galaxies in there.
Okay.
But now Spider-Man has come up and people have been saying stuff like, oh, yeah, I mean, what if there's, and this fellow, Stephen Hawking, he also made this multiverse hypothesis because it still hasn't been, he made this thing popular where he said that there might be a universe out there where you are probably dating Emma Watson. Yeah, I mean, unfortunately, we are not in that universe, but okay. Like as they say, our universe is like one of those universes where if something goes wrong, it will go wrong. So probably because of that, we haven't had the opportunity to Watson yet.
So our universe is
But,
like
yeah.
the leftovers. All the bad things will happen in this universe.
Probably, I'm not sure. I don't want to say anything like that because
You don't want to jinx it.
Yeah, I don't want to jinx it because then if something wrong actually happens, then people are going to be like, "Ye bande ne bola tha." This was the guy who said that, and this guy is the problem figure. Just get a hold of this fellow. So yeah. Now coming back to the topic.
Oh yeah, I actually wanted to ask you.
Yeah.
You said that we are living in a city, unfortunately. So were you born and brought up in the city?
Yes. I was born and brought up in Bombay, and unfortunately, I never saw the stars. But then again, my universe changed when I went for one stargazing, and that night changed my life.
Okay.
And that is this moment of like in my dark times. That's the moment. That's the moment where I go back.
And also, when you saw the Milky Way, who were you with? With your friends, with your family?
Yeah, with my friends. We were 5 people from my college. And we had no clue how to use the telescope, and we figured it out within like a night. So it was part of this course that I was doing from Nehru Planetarium. So one of the things that is good is your local planetarium would have courses where you go and they will teach you about basic astronomy, and they also have stargazing events and everything. Happens with every planetarium. So you could like reach out to them. It's kind of their job to popularize astronomy. So that's what they do. So yeah, I did that, and fortunately, I was exposed to a beautiful universe out there. That kind of the way I think.
And what was the reaction of your parents when you told them that I want to make a
They were
living
like,
out of
"Why?"
looking at stars?
Yeah, it was as good as coming out to your parents and being like, I like guys. For a,
So
they
it's
were
so
like,
they didn't.
so my son is not. My dad was like, मेरा बेटा पैसे नहीं बनाने वाला. My son is not gonna make money. So do whatever you want. So they started making money so that my future is kind of safeguarded.
Oh my god! Okay. And are they now like
They are
on
cool
your
with
side?
it now. Yeah,
Now they are cool with it.
Now they are cool with it. Much more cool than before.
Okay.
Right? Initially they were not, and there was quite a lot of resistance because they were like, "Hey, why not become a doctor, dude? Something that pays your bills and all." But then I was like, "Okay, bills. I mean, I need to ensure that I make enough to pay my bills. But other than that, the rest is just, I would say, useless for me. So the excess money is kind of useless. So I might as well make enough so that I can make a living out of it and then continue with the passion." So,
And also about looking at stars, I think it would be nice if I let the listeners know that you are not just someone who looks at the stars, but you have also done your masters in astrophysics. So that's not something.
Yes, I've done my masters in physics, and my project was in astrophysics. But the thing is, astronomy was something that was never taught officially. So whatever I learned through Google, and trust me, the things that you can learn through Google these days is just blows my mind, because make use of the resources that you have. So yeah, I made use of that and I learned astronomy.
So you had your masters in physics, but you did your master's thesis in astrophysics.
Yes, in astrophysics.
Can you talk a little bit about your thesis?
So my thesis work was on neutron stars. So it's basically, think of neutron stars like nuclei of atoms. Just to give you an idea of what scale we are talking about. Take Wankhede Stadium, right? If that's your nuclei, take the cricket ball that you have, right? Keep it at the middle of Wankhede Stadium. Okay, that would be your nuclei. That's where all of your mass in your body is concentrated, and electrons be sort of like, you could say, flies on the pavilion. And the entirety of Wankhede Stadium would be the atom. So you're mostly empty space. And most of your mass, all of your mass actually, is concentrated in that nuclei. Right? And you're made up of trillions and trillions of such atoms. Take that nuclei and make it a 10-kilometer big nuclei in real life, okay? And a nuclei which is that big, right? A neutron star is somewhat like that.
So it's not, just to correct you a little bit, it's not that the nuclei is getting bigger. It's just that it's the number of things in it is increasing.
So it's basically, you take a nuclei the size of almost half a cell.
Okay.
Okay. And what you do is, you have the nuclei at the center, right? The density of that nuclei, you take a ball which is that big, right? 10 kilometers big, right? And the density of that ball would be comparable. A very, very solid ball. And that's what we call as a neutron star. A neutron, why? Because it's primarily made up of neutron. The outermost layer is kind of that. It has a very thin layer of iron on top of it. Okay. But most of it is just neutrons, and majority. And that's why it's called the neutron star. And my work was to study neutron stars around stars like our sun. Right?
Neutron stars around stars like ours, which are in a binary system with
in
a
a
star like
binary
our sun.
system. Yes. Basically, think of them going around each other, or rather, the neutron star going around the main sequence star. That's what we call it, a star like our sun, just primarily burning hydrogen. And imagine the nuclei with a 10-kilometer big sphere. Nuclei, big nuclei kind of sphere, super dense sphere, which is going around the star, and almost the mass of that is almost comparable to the mass of our sun. Actually, a bit more than that, but fine, right? And what happens is, when these kind of things, they orbit each other, right? And that neutron star is actually very close to the host star. That's what we call them as, right? They take in a lot of matter. right? Imagine like वो toilet flush करते हैं. You know what happens over there? Like it siphons down and there is a vortex kind of thing.
Yeah.
So a similar thing kind of happens with the neutron star, right? It siphons matter from the star into it. And this thing technically is called accretion. And when this accretion happens, it emits a lot of radiation. But most of it happens in X-rays. So what my work was to detect those X-rays that comes from a system like that, a binary system like that. And do loads of fun stuff with that X-ray. So yeah.
Like what fun stuff?
What are the things that we are looking at, right? There are two particular things that you can see in a system like that, right? Either you can see how that system is being. So you look at these things called light curves, meaning how the brightness is, okay, and or like through time, and that tells you a lot about what is like how fast is it orbiting, right? The star that I was looking at, 1A 1246588, the name, right? Astronomers have beautiful naming conventions. So the star that I was observing, or rather the binary system that I was observing, had an orbital period of around a day.
A day. So it would complete one orbit around its sun star in
so
1 day.
1 year would be worth 1 day.
More than fast.
Fast.
Saying fast would be another statement.
Very fast. Just imagine you will have your birthday every day.
Wow.
So just imagine that would be fun.
One specific minute of the day is your birth minute. You would have birthdays. You would have birth
minutes. But then
minutes.
nobody celebrates 1 minute.
1 minute of your birthday.
Hey, happy birthday. Hey, happy birthday, auntie. No. So like birthday is a day. Right?
Okay. And
almost a whole day.
When you're talking about light curves, is it?
Yes. So when we are looking at light curves, what we do is we look at X-ray light curves.
Okay.
Right? Because when these things they accrete, they emit a lot of radiation in multiple different wave bands, or rather in the whole electromagnetic spectrum, in multiple different wave bands. Like they emit in radio, visible, infrared, UV. But most of it, the majority of it, happens in X-ray.
Okay.
Right? The peak happens at X-ray. So what I do is I look at those X-rays, and what you get from that is you look at the orbital period. You can get the orbital period using X-rays only. So when I plot the light curves, I use X-ray light curves. I mean,
okay.
Now there is a bit of gamma rays as well, but it's not as much. But most of it is X-rays, and that's why they are called X-ray binaries. Because binary, because there are two stars in it, and X-ray because they peak at X-ray, right? And that, and then we look at the spectrum as well, meaning that Newton ne jo kiya tha na prism ke saath, that whole Vibgyor thing. So we look at the Vibgyor of X-rays, right? And that is, I would say, much more fun than looking at the light curves, because light curves, the amount of things that it can tell you is quite limited compared to the things that you can see from the spectrum. Right? The spectrum tells you what is the star made up of. Okay, what is the host star made up of? What is the neutron star made up of? We see a lot of radiation from nuclear fusions, or rather like Hiroshima, Nagasaki kind of explosions happening on the neutron star's surface every second.
Every second.
Yeah, every time something falls in, matter falls in, it emits a lot of X-rays. Why? Because there are nuclear explosions happening on the surface of the neutron star.
Also, talking about going back to when we talk about how the orbital period is just 1 day, which is really fast. So, won't the neutron star just go out and just elongate due to the tidal forces?
The thing that if I'm getting you correct, what you're talking about is centrifugal force that is causing the neutron star to fly off.
Yeah, not fly off, but it will
but it can
elongate into
So elongate as in the orbit, you mean?
Yeah, like it will stretch a little bit.
So the dimensions of the neutron star, or
the dimension of the neutron star.
The dimensions. So the thing is that because it's so dense, and it is like a 10 kilometer sphere. I mean, like Earth itself is what, like 6,000 kilometer radius.
Yeah.
12,000 kilometer. That approximately is the diameter, right? This is 10 kilometers.
Okay.
And it is equal to the mass of the sun. Alright. So if you are like, say for example, you want to imagine how big the sun is. Take your fist, right? If that's the Earth, then the sun would be the size of a 10-story building.
Okay.
Just to give you the idea of the scale, right? Imagine all of that mass concentrated into a point, actually more than that, but concentrated into a point which is smaller than a city.
Okay.
So that's the kind of density we are talking about. And when you deal in densities like that, when you deal in concentrated material like that, or super dense objects like that, their gravity is very high, right? So high that it essentially does not care about any kind of center.
Okay.
So it maintains the shape of it, right? Yeah, of course, the shape wouldn't be maintained. Say, for example, you look at tidal effects in Jupiter's moon.
Yeah.
Right? The shape is not maintained. Why? In Jupiter's moons, where like Io it stretches a lot, right? Why? Because there's a lot of tidal effects from Jupiter. Jupiter is huge, has a lot of gravity. So the side of Io that is actually pointing towards Jupiter, right, experiences more gravity than the side of Io that is facing away from Jupiter, right? So there's quite a lot of tidal stretching that happens, right? But then the neutron star is so dense that this tidal stretching is negligible. Rather, the host star has a lot of tidal stretching.
Oh wow!
And that is the reason why matter siphons in from the host star into the neutron.
Okay.
Right? There is this thing called Rochelle Overflow that we kind of need to take care of. It's basically a dumbbell kind of shape that forms around two orbiting objects. Right? You have one object on one end, one center of the one lobe of the dumbbell, and the other object at the other center of the other lobe of the dumbbell. Right? If any matter from either of those stars exceeds that limit, exceeds the shape of the dumbbell, because the lobes are equal sized, right? Both the sides are equally big, right? So if one of them is too big and another one is very small, so anything that is beyond the dumbbell, what happens is when that thing overflows, when there is any matter which is outside the Roche lobe, right, it flows into the neutron. And when that happens, right, we have this thing called accretion. And these two lobes, they change in sizes based on how far the neutron star is. Now, say for example, if we had a neutron star, same case in our solar system, if we had the neutron star which is at a distance of say Pluto, then we wouldn't have any kind of accretion. But if we had a neutron star say closer than Mercury, in case of our sun, then we would have easy accretion. And then what we would see in our sky is two big jets and a lot of X-ray.
And I'm pretty sure we would see that for like 2 seconds before everything goes black.
No. We will see that for several. I think so. These are not like happens for like a week, or not like supernova that goes off and then stays there for like a week or two or like that. These they go on. They go on for way longer than that, like 2 years, 3 years, 4 years, 5 years. It can be anything. Depends on how close the neutron is. And the fun fact, there are certain times when the neutron star can be inside the host star as well.
Wait, but if it's inside the host star, it is the host star. Like, how is it separate from the host star then?
Yeah. It's not. And the thing is, it does not show up on our detectors. Right?
No, because it's inside the star.
It's inside the stars. But we see, when we look at the spectrum of the star, we see a lot of, variations in that spectrum. By variations, I mean a lot of absorption happening, then a lot of distortion that's happening, then we see a lot of an unusually large amount of X-rays, because when it's inside the host star, right, it's accreting a lot of matter. Right?
Why does it need to accrete the matter? It's all around.
It's inside, but then matter is falling in now. At the end of the day, it's falling into the neutron star
from inside the star.
Yeah, I know that does not make sense, but there are objects like that out there as well, but most of them are very rare, and you don't see them every day, and you need to look at the spectrum. So one of the reasons why I say spectrum is much more interesting is you can see stuff like that in the spectrum of a star. Right?
You won't see that in an optical spectrum.
No, you won't see it in an optical. You won't see it in X-rays and UV. Mostly in UV. You will see those distortions. Right? Okay. It will look like a normal star. Right? When you look at the spectrum of the star, it will look like it's just a normal kind of star. Right? But when you look at the X-ray and UV spectrum, right, you will see certain distortions that can only happen when there is some sort of accretion happening. But you do not see the companion. So you are like, there is no companion.
Where is it accreting to?
What's the accretion that's happening? Like where on earth is that accretion happening from, and
to what? To what? Yes.
Like to what? And that is when we know yes, these specific objects out there they are actually neutron stars inside the host star. But they are very, very rare. And it happens mostly with giant stars. Coming back to the normal stars, there are very, very wide range of things that you can say, like stuff like this, right? Just by looking at the X-ray spectrum of a star. And that is kind of the reason why I look at X-ray.
Also, you mentioned gamma rays.
Oh, yes.
Before. And I know that you have also worked a great deal in detecting gamma rays from supernova stuff and things that blow up in the sky.
Those are my postmasters.
Your postmasters. Can you talk a little bit about those?
Yeah. So, after masters, I was like, these neutron binaries are fine, but the thing is that there are different kinds of astronomy. Like, there are many. There are 3 pillars of astronomy, so on and so forth. But coming to observational astronomy and astrophysics, you have transient astronomy and then you have non-transient astronomy. Transient means things that you cannot predict. Okay, that's what we mean by transient. So, say for example, if I do it with my students, where if they show up and there is no way to predict when they would show up, I'm like, "Tum transient source. You're a transient source because there is no way for me to tell whether or not you will show up at this particular time." Basically, it means any source that is not predicted. And non-transient astronomy is everything else. So you look at pulsars, you look at stars, you look at anything which is predictable, and then you can see with pulsars, you can see, a very predictable amount of pulses per second. So those things, those fall under non-transient astronomy. And the thing with non-transient astronomy is that you have to write these very, very beautiful human constructs called proposals, right? The data is not freely available. Whereas in transient astronomy, since there is no way for you to predict from which end you would get or from which direction in the sky you would get the data from, you do not need to write these things called proposals. So that was kind of the reason why I joined transient astronomy, because I was like,
you would need to write proposals.
Yeah, I don't have to write proposals and the data is freely available to everybody.
Okay.
Right? And there are good sides to it and bad sides to it. Good sides is you don't have to write proposals. Bad side is now everybody has access to the data and everybody starts to work. So if a supernova happens, supernova is basically when a star dies. A star, not just any star, like our sun is like meh. But star, say if I replaced that star with sun, then star which would span the size of almost Earth or Mars star. It's that big. Those are called giant stars. And when these giant stars, red giants, blue giant, super giant stars, when these stars die, they give out a lot of radiation. Gives out a lot of radiation. But when these stars die, they give out enough radiation to outshine the entire galaxy for like 2 weeks. Just to give you an example, if a supernova happened in our galaxy today, first of all, there is no way for us to predict, so it might happen in the next 5 minutes, or it would look like it was another star or rather another sun that appeared in the sky. For example, Chinese astronomers, I think so it was 1400 or 1300 BC AD, they discovered this guest star that appeared in the sky for like 2 weeks, and it was like this another sun in the sky for 2 weeks. Later on, turns out it was a supernova that had happened around the same time, and now we see it as this thing called M1, which is known as Crab Pulsar or Crab Nebula.
Yes.
So that's a supernova remnant. And just imagine you go out and you will be sunbathing for the whole
week. For the entire 2 weeks.
Like every day for the entire 2 weeks. But yeah, it's quite a fun thing to imagine. So the thing is, that's how bright a supernova can get. That too, it's happening at probably some other end of our galaxy, not even close to our sun. And these things are so bright that within the span of 2 weeks, it emits equal or rather more radiation than sun would emit in its lifetime.
Oh, wow.
So it's like for 4, 5, 6, sun is a main sequence. So 6, 7 billion years. That entire
in just 2
lifetime,
weeks.
Yeah. In that 2 weeks, it emits equal or more radiation than that. Entire light, all the light that sun is going to emit in its entire lifetime, take that and cramp. With transient astronomy, the thing is you have to be on your feet. That's what I like. And if the data shows up, and these data and everything that comes to me every day, almost I think so. I got 3 emails today because there were 2 supernovae that were detected today in some far corner of our galaxy. Star Wars reference. In some corner of what was it?
In a galaxy far away.
In a galaxy far away. Yes. The first one happened at I think so 11:30 today morning.
Today morning.
Yeah. And the second one happened, I don't know, like they haven't mentioned the exact time, but probably around 6 to 7 p.m.
Then why didn't we?
Oh, no. We can't see it because it's in a galaxy far away, right?
Okay.
If it
so it has to be in the same galaxy.
If it happens in our galaxy, in any corner of our galaxy, we would be able to.
Okay.
Right? But since this happens in galaxies that are way in the past, the light takes a lot of time to reach us. That's why it's in the past.
Yeah.
It's very dim. So that's why we are not able to see it properly. But if you want, you can look up images of supernovae happening in different galaxies, and then there are quite a lot of people who actually observe those things. And they can actually see. And there was this one supernovae that happened, 190829A. And it happened in a spiral galaxy. And this is a supernova that I worked on. And it was so bright that people actually photographed it.
Okay.
Right? And they kind of saw, like they saw the whole galaxy, and then they saw a star appearing within the galaxy. And then that was like, oh my god. So basically, I look at those kind of stuff. I look at mostly transient astronomy stuff. And look at gamma ray bursts, that exact technical jargon that I'm trying to use over here.
And what do you do? Like, as you said, from X-rays, you can figure out all these fun stuff.
From X-rays
from
and
gamma rays,
and
what
everything.
fun
from
stuff?
Gamma rays, first of all, the fun thing that you can do is you can name your photons, because we see 1 or 2 photons. So we are like, that's Tom, that's Jerry, and this one is Brutus. So we can name our photons. But with that as well, what we can do is we look at the spectrum. The spectrum tells us stuff like, okay, the star died. What was the mass of it? We talk in terms of energy, right? So when you are talking to a radio astronomer, they would say, okay, we took a 10 megahertz, 10 hertz, 20 hertz, 30 hertz, very low wavelength, very high wavelength or low frequency observation, right? So radio astronomers, they talk in terms of hertz. Gamma ray astronomers, X-ray astronomers, we talk in terms of energies, because after a while, light has a beautiful thing where it has dual nature. It behaves like a wave in certain parts of the spectrum, like in radio and everything. It behaves more like a wave. When you go to visible, you can explain it both using you can explain it both using waves and particle. And with X-rays and gamma rays, the frequencies are so high, meaning the wavelengths are so low, that it mostly behaves like particles. And when you're talking about particles, every particle has an energy, right? And it also has, like, what you can do is you can calculate the number of particles that are colliding with your detector, right? From that particular direction. So that's why what we do is we look at energies all the way X-rays, which goes on to soft X-rays, which goes from 0.3 kilo electron volts to 8 kilo electron volts, and hard X-rays, which goes beyond from 8 to 100 kV. So you just convert that into, Planck's law. You convert that into wavelength, and then you will get the exact wave. So that comes out at around 0.2, 0.3 angstroms, something like that. So we look at wavelengths that small, and what that tells us is quite a lot of interesting things. Like, it tells us what was the composition of the star that died. What is the composition of the stuff that the light had to pass through?
It was in between us and the star.
And the star, yes. So we call that interstellar medium, intergalactic medium, right? Because these are happening in different galaxies. Then the star, the radiation also that comes from the center of the star, which dies, right? That has to go through a lot of matter, which is outside the shell of the star, right, which is not part of the core. So it has to go through all of that matter. So it tells you how the elements and how the star, what was the mass distribution of the star. These are the things that you can know from looking at the spectrum. And it tells you what was the composition of the star at the innermost region, what was the composition of the star at the outermost region, what is in the middle region of the star, so on and so forth. So it tells you a lot about how the mass was distributed of the star, how the mass of the star is generally distributed, right? That you can connect to sun and be like, oh, so then probably if this star was something like this, if the mass in the star was distributed like this in this big star, probably a similar story would be seen in our sun's case as well. But that's the reason why one of the biggest struggles that we have is, how do we know that the sun has different layers? How do we know that sun is burning helium at the center? How do we know what is the metallicity, or rather what's the composition of the elements within our sun? Right? How is that composition? How does that composition change from when you go from the center of the sun to the outermost, the photosphere? That's again jargon. Yeah. Because sun is mostly opaque, right? Light doesn't pass through it freely. You point a laser at the sun, the light won't be reflected, right? So that's why they call it a black body. I know it's kind of like sun black doesn't make sense, but yeah, sun is essentially a black body. It has its own radiation, but it absorbs everything that falls into it. So that's kind of why we call sun a black body. So it's very difficult to probe the insides of a star, right? But with gamma ray astronomy, with X-ray astronomy, mostly gamma ray astronomy, what you're able to do is probe those inner regions. Think of it like this, yeah? When a star dies, right, every big star that dies gives out some sort of gamma ray burst. Alright? And these bursts happen at very specific angles, and they are very, very narrow beams.
So it happens at specific angles.
Yeah.
It doesn't happen like a spherical wave.
Yeah, it's a spherical thing, yes, but what happens is, because the star is so far away, there is this thing, and again it's moving away, there is this thing called relativistic beaming that happens. So the gamma ray, when it comes out from the star, it goes out in all the directions, right? But when it comes to us, it appears like a very narrow beam. Why? Because relativistic beaming.
Okay.
Length contraction along the line of sight, basically. Okay. There is all the gamma rays that we see. It's basically what happens, like relativistically what happens is it creates an effect that causes it to look like it was two beams of gamma ray bursts, or rather two beams of gamma rays that came out from the star. And the thing is, it all depends on how the galaxy and the star is moving compared to us.
Okay.
Right? So, the thing is that whenever you look at gamma rays, or rather gamma ray bursts, first of all, there is no way for you to predict it. But, now, if a supernova happens within our galaxy, alright, and this angle, the supernova, the beaming angle, is such that it points towards us, it can fry our entire Earth, even if it passes very close to the solar system, not even like, just grazes through our solar system, it will fry our entire atmosphere within a few minutes. And it's again beams and relativistic beaming, right? And it will fry, and so if you suddenly start feeling extremely hot and your skin starts to melt, it's probably a gamma ray burst. So
only if it's in our galaxy. So
only if it is.
Let's hope it doesn't happen.
If it's within our galaxy, even if it happens in Andromeda galaxy and the gamma ray burst is pointing towards us, then we would see a very bright flash of gamma rays, and it will probably nuke all our satellites. But again, these are very, very rare occurrences, and these are just two galaxies, Andromeda and Milky Way. There are trillions of galaxies out there, so that's the reason why you see one or two every day.
Okay.
Right? And
even after having trillions of galaxies in the universe, we only get one or two. But that doesn't mean that they are not happening. They're happening all the time. It's just that the beaming angle is not towards us.
Yes.
Yeah. Okay.
So again, the beaming thing happens for two very specific reasons. One is, yes, the gamma ray emits in all the directions, right? But there's quite a bit of beaming when it leaves the star, and which is further beamed because of relativity, because of its relativistic motion. So there are those different kinds of beaming that happen. Now you can sort of see that in our detectors as well, and that's what's fun.
Okay.
So yeah.
And you're still going at it. You're still working on papers.
We look at gamma rays every day, and the thing is, with transient astronomy, we don't just look at one gamma ray burst. We look at multiple gamma ray bursts. So one paper, like the last paper that we did, that had around 100 gamma ray bursts, right? Almost around 94, 95 gamma ray bursts.
Okay, and these were taken from like all the previous records.
Yeah, previous records, previous gamma ray bursts, where we took similar looking gamma ray bursts compared to the gamma ray bursts that we were looking at. That's 1908-29. So yeah, we looked at similar gamma ray bursts, and similar two peak gamma ray bursts, because then there are these things where this is where the light curve comes into play. Is that some gamma rays have one big peak, so there's a big boom that happens. The brightness goes up and then it slowly decreases over a span of a few seconds. From few seconds, it can go like there are long gamma ray bursts, there are short gamma ray bursts. Long ones can go up to 100 seconds, 200 seconds, right? Short gamma ray bursts, and they are usually like the long ones are actually a bit dim compared to short gamma ray bursts, which happen at around 1 second, or rather 0 seconds. 0 seconds is not possible, but from 0 to 4 seconds.
Okay.
So sort of like that. Like that's a time period.
It's a very small.
It's a very sharp burst of gamma rays that we see.
And also, I wanted to ask that because it's a small time frame, they reach us. Gamma rays, their photons reach us very quickly.
As you had said, the supernovae, they happen for over weeks.
Yeah.
Right? But since they are so far away, there is this thing called time dilation.
Yes.
That entire 2-week duration, because of time dilation, gets compressed to 1 second, 2 seconds, 3 seconds. Something like that. Right? And because it's moving far, it's moving very, very fast away from us. The further a galaxy is, right, the faster it recedes. Very fast, like almost 0.1, 0.2. Sometimes, most of the gamma rays that we see, they happen at very high redshift. By redshift time,
the star is very far away.
Very far away. Right? And that tells you how fast it's from us.
Yeah.
Right? So, whenever some gamma ray burst happens, it happens at that, if we were close to the star, if we were within the host, that star's galaxy, we would see the sun, the extra guest star in our sky for like 3 weeks, a month probably. But for an observer which is very, very, very far away from that galaxy, they would see it happen within a few seconds.
Okay, yes.
That's kind of what relativity does to the data. So there's quite a lot of relativistic effect that we need to account for, and all of that, again, we do it using the spectrum, but this thing is done mostly by looking at the spectrum, looking at the Doppler shift, and then from that telling ki this is the time period, this is the duration of the actual gamma ray burst that happened. So the actual one might have happened for like a month, and we are just seeing all of that happen in like a few weeks, or not a few weeks, sorry, but a few seconds, or 2 seconds, 3 seconds, or something like that. But there's one interesting thing as well. Like, it's not always that a star dies that we have these things called gamma ray bursts, right? We have these different kinds of gamma bursts, right? When there are two neutron stars, for example, they are colliding with each other, right? We see a gamma ray burst. When there's a black hole neutron star, not really. We don't see any gamma ray bursts. We see darkness. Right, but
so we can actually see that this star was here and now it's gone.
Yeah, but we haven't actually seen something like that because we have neutron star binaries, but we cannot see neutron star binary. Like, we cannot even see a neutron star because it is that small. Right?
Okay.
We can see its effect in the spectrum of the host star. We can see if that neutron star is absorbing, or rather accreting, a lot of X-rays. We can see that, right? But we cannot directly image a neutron. Just like
unless the neutron star is a pulsar.
Yeah, I mean, yes, of course, like if a neutron star is a pulsar, then it will show up as pulses on the radio spectrum, right? In microwaves or whatever you want to call it.
So we can use those pulses. So right now we are seeing those pulses, and now the pulses are gone. So maybe the neutron star was taken in by a black hole, by its binary black hole.
Yeah, probably. That can happen, but that hasn't happened yet. Because for that, what we need to do is observing pulsars in galaxies far, far away is really difficult.
Okay, an idea for upcoming astronomers?
Yeah. And James Webb is gonna.
Oh, yes.
Yes, James Webb is gonna what? Like 25th? It's launching on 25th. Yeah, and Christmas Eve. So let's hope everything goes right because that guy just got delayed for like how many? I think some 4, 5 or something years. I'm not sure how many years, but it has been delayed a lot. So we hope to that it doesn't get delayed anymore. And the launch date is on December 25th. So and I just hope that everything goes well with that. But if that happens and if they are able to send it and put it in not orbit but in the Lagrange point, topic for another discussion. If they're able to do that, then we could see pulsars, or rather not pulsars, but we could see neutron star binary system in within our galaxy and within say Andromeda galaxy, right? Because the way we see neutron stars, just like black holes, have never been directly emitted, right? Because they are very small and they are very tiny. Right, and the only way to see these compact objects is through the immense amounts of radiation that they are giving. Whether in X-rays, whether be it in radio. If there is a neutron star which is just rotating by itself, these neutron stars they rotate in like what?
There are millisecond pulsars.
Yeah, like almost 100 times a second or something like that. Right. So these things they rotate very fast. So we see pulses, and that's how we know that there's a neutron star over here, right? If we see pulses, very, very specific pulses from a particular direction in the sky, we are like, okay, fine, probably there's a neutron star over here, right? Another way of imaging neutron star is when it's accreting matter from another star, right? That's when we see neutron stars. Then, given the whole LIGO thing that has come up, if we have two neutron stars orbiting, or say a neutron star black hole orbiting, or two black hole orbiting, then we can see their effects in the gravitational wave, like the gravitational wave that they are giving out. We can see those things from our telescopes, like with LIGO and Virgo and stuff. So yeah, I mean, till date there is no direct way of imaging neutron stars, unfortunately. But given James Webb, okay, who knows? We might get a few interesting results. But then James Webb is mostly in UV, IR and visible. So let's see. Let's hope for the best. But yeah, I mean, mostly it's very difficult to directly see a neutron star. But yeah, it's just like white dwarfs. White dwarfs are also very difficult to see. But then white dwarfs are like Earth-sized stars. Like take the entire mass of the sun and compress it into the size of the Earth. And that's roughly how big a white dwarf is. So they are quite big, and they are bright as well. So that's why we are able to see white dwarfs pretty easily. But still, it's very difficult to see white dwarfs. So neutron stars are even more difficult to see, right? Unless you have some sort of interaction. So yeah.
That's actually really cool and really interesting. So I also had a few questions which were, in general, your experience as an astronomer, as an astrophysicist, as a physics person in India. So as you said that you were born and brought up in the city and your parents weren't really with you when you...
In the beginning, of course, like Indian parents, it's either doctor, engineer or something. So either bono doctor, either bono engineer. Asian parents, if I'm not wrong. They don't count dentists as doctors, but fine for some reasons. But like that. So the career options are pretty limited. So anything that deviates from that, specific career path, it would be really difficult for you to get, your parents' approval for that.
But now they are with you.
Now they are, because they are like,
So is it not because now they know that you have worked so much in all these research fields and you have published papers?
Yeah, they don't know about my paper. They know that I have worked. They know I have published papers, yes, but they don't know what exactly I work on, because the moment I start a little bit of astronomy with them, they are like, "Arey, bas ho gaya yaar. Tum pura din bajte rehte, tum apna karo na." Do you see? So both my parents are bankers. So they are like, do you see us talking about banking and everything with you? No, so then shut up. I'm like, okay, fine.
But still, apart from that, you were able to complete your masters. You have helped publish so many papers. There was one thing which I wanted to ask you, is that people think of a scientist as someone who is always like, in the books and who's always writing equations, with all those curly hairs.
Yeah,
thanks to media. So that is what the image of a scientist is for most people.
For most
But
people,
how is it different than an actual scientist?
Oh, actual scientist is like a normal person here. I mean, सुबह को उठते हैं, we go to the loo, we brush our teeth, we get up, then we think, why does this earth exist? Then we think, why doesn't everything just get destroyed? Like, just because of a gamma ray burst, we pray for a gamma ray burst for like 10 seconds in the morning in the loo. Then your girlfriend calls and then you're like, oh my god, this is so nice. And then you're back to reality and stuff happens. So the thing is that scientists, just like any other person, right? Like Jeff Bezos, Elon Musk, we are all people at the end of the day. So, we take a shit in the morning. So,
but do you think, are there any things which are kind of true to what they show in the media? Are there any Eureka moments that happen among the science community? Never?
The Eureka moment, the last Eureka moment that happened with me, or rather the fun moment that happened was when we were working on the last paper. And I remember that the reason why transient astronomy is so much fun is because when you get an object, you have to work your butts off on that. And because there are multiple teams working on it. So the moment you find something new, the fun part is you now know something that nobody on this planet knows. And now it's your responsibility to tell everyone. So that's something that I believe is really beautiful and keeps the spirit of science alive, because just for a few fraction of seconds, you know something that nobody on this planet knows. And that is kind of, and which like, of course, there are personal things as well, but that's just a very fraction, that fraction of moment, that's what I live for, you could say, that's what makes science fun, because you have discovered something, you have discovered, even if it's like a very small thing, but you have discovered something at the end of the day, and that's what we, then we slog our butts off for like 6 months, 7 months.
Oh wow.
And then we try and tell everybody on this planet how exciting it is, which probably only 10 people on this planet read. And 2 people probably find it interesting and they are like, okay, we can do further work on it. That's when we get citations and stuff like that. But it's all about, at the end of the day, we all want to know where we come from. We all want to know why we are here. So it's just our own way of doing that, giving meaning to our seemingly meaningless existence. So, that's kind of the reason why we do it. So, like in media, yes, the Eureka moment where I think so it was Archimedes who, when he discovered that
water has volume.
That thing, his principle, he ran naked through the streets of his town. And some people say it was Athens. So the evidence is, I'm not sure how compelling that evidence is, but the town, and people say that he ran naked through the whole thing, because that's the kind of thrill that we get. Even if it's like within 4 or 5 people, it's a thrill nonetheless.
Talking about thrill, as you just said, that sometimes you guys slog for 6-7 months.
Yeah.
So, does the thrill stay with you for the entire duration?
No. That thrill lasts until your co-author says something like, but are you sure? And that's when the thrill dies, and then a new thrill emerges. So it's just like.
So how do you keep yourself going? That once you start, you detect a GRP, and now you have to tell it to everyone. For that, you have to write a paper.
Yeah.
And so, as you said, the thrill dies out after some time. So, how do you keep yourself busy with the paper? That, no, I have started this. I have to finish this.
No, that's when this thing, very interesting human thing that comes up, which is called grit. It's like, even when the world looks bleak and everything doesn't make sense, you still keep going. And that's how we get to a point, right? After a while, you just don't let things go, right? This is one of the things that I loved about Einstein and all scientists that I've met till date, is that, and that's something that I aspire to do, is never let go of a problem. Say, for example, you encounter a problem that comes up in your mind and, you're not able to solve it. Don't let go of that. Don't give up, whatever, mere se nahi ho payega, just let it go. No. Lage raho, just keep at it and you will find something. Probably something that you expected, or probably in most cases, something that you never expected. So that's how I believe scientific development and advancement happens. You just keep at it. You just do not let it go. So you keep reminding yourself, hey, look, why am I here? What am I doing? What's the meaning of this? And within that 6 months, you will have several mental breakdowns. Happens. You start questioning your existence. Why am I even doing this, man? What's the point of this? Then you take a few days ka break, 1 or 2 days ka break लो. तीसरे दिन फिर से काम पे शुरू. Okay. So point is, you just don't let it go. It's a test of grit. Like how much you can persevere even when the world looks bleak. So you just keep doing that. And we do it for science, but I believe everybody does it for their own thing. I mean, bankers do it, philosophers do it all the time, business people do it. Elon Musk had a beautiful quote where he said, the fun bit is just that moment, and when that moment passes, you come back to reality. That's when, actual work starts, and that's where you're actually tested. So in order to have those fun bits, you have to go through those bits as well, right? In order to have 4-5 moments of intense dopamine rush, you have to slog your ass through
6-7 months.
2, 3, 4 months. One of our papers happened within 2 months, and another one took like 6-7 months. One took a year because we were lazy, both of us. So we were like, okay, fine. Let's just, let's let others do some work on it, and then we will, work a bit more on it. So like that. But yeah, it's all about the test of grit and how much you are able to persevere. That's kind of the reason why I believe that science is not everybody's cup of tea, and that's completely fine, because banking is not my cup of tea. Music is definitely not my cup of tea, because I can't hold a note. And you ask me to slog like even 5 minutes, 10 minutes in music, I'll be like, "Arey yaar, bas ho gaya yaar." So like that, art is something that beats me completely. So stuff like that. So you find your niche and just look at how. Just find that niche and just keep going.
Just keep going.
Do not stop, no matter what.
It's about drive. It's about power.
Yeah. I can't say how many times that particular song has inspired me to keep working. And I'm like, Subha was like every day morning. There was a time when I used to listen to similar songs, not this exact song, but I used to listen to similar songs just to wake up and just do it. And most of the time, it's just brain dead work that I'm doing. It's just plotting stuff, plotting the spectrum, and so on and so forth. And it takes a lot of time. So what I do is I do other stuff during that. So mostly it's just that. But unlike what the media portrays, it's not like we don't wear lab coats all day. Most of us have, but we don't have spectacles, right? We don't look nerdy, like for God's sake, I have tattoos and a skull ring. But stuff like that. But yeah, they can't see me, so okay. So one of my students said that, so you don't look like a scientist. I'm like, oh yeah, sure. What does a scientist look like?
You look more like Kabir Singh science version.
Yeah. Like Kabir Singh might OD someday or something like that kind of fellow. But yeah, I kind of look like that. I've been told that actually, because one of my professors, he was like, the first time I met you, you looked as if you were some sort of like some fellow who did illegal shit and everything. So like some dicey fellow who would be like, hey, idhar drugs milega kya? Why type of fellow? But I mean like that. But at the end of the day, we are all people. We are all human. So there is no particular way a scientist looks like. We are just normal people. So yeah.
Thank you so much for giving me your time.
Thanks for having me.
Thank you.
Hope you loved the episode. Subscribe to our show and see you next Saturday.